The biting cold near Lake Superior was a harsh teacher for Samuel Morrison during his first winter in 1846. Despite feeding his fireplace with 3 cords of wood, his cabin remained frigid. He had meticulously followed the standard homesteader's practice: a stone fireplace, a straight chimney, the conventional and trusted method. By spring, he had burned an excessive amount of wood, far more than should have been necessary, as precious heat escaped uselessly up the chimney. Across the northern frontier, settlers faced the same frustrating problem, their textbook-built heating systems failing season after season. Samuel, however, quietly innovated. He dug an underground tunnel to capture smoke and store heat in the stones beneath his cabin floor. His neighbors scoffed, deeming it an unnecessary and extravagant effort. But when winter's icy grip returned, Samuel's cabin remained warm for a remarkable 36 hours on a single fire, while his neighbors shivered through nightly freezes. What insight into heat storage did he possess that eluded every other frontier builder? Samuel Morrison had arrived in the Michigan Territory armed with the same manual as every other homesteader, the Army Corps of Engineers Guide to Frontier Construction, printed in 1843 and distributed at land offices from Detroit to Duluth. The manual's instructions on heating were unambiguous. Build your fireplace against the gable end, construct a straight chimney to ensure proper draft, and trust the open flame to warm your living space. Every territorial agent, lumber camp foreman, and established settler echoed the same advice. The method had proven successful in Virginia and Ohio, so it was expected to work on the northern frontier as well. Samuel had followed these instructions to the letter. His fireplace, constructed from local field stone and mortared with clay and sand, measured 4 feet wide with a 14-inch throat opening. The chimney rose 18 feet above his cabin roof, capped to prevent downdrafts. Before the first snowfall, he had diligently split and stacked 8 cords of dry maple and birch, exceeding the manual's recommendations for a cabin of his size. Everything was in accordance with regulations, everything was supposedly proven. But the regulations failed to account for the peculiar and penetrating cold that settled over the Great Lakes region. When December winds swept across 200 miles of open water and slammed into his cabin walls, the interior temperature plummeted 20 degrees in a single hour. Samuel would stoke his fire until flames danced 2 feet high, yet the heat rushed up the chimney, disappearing into the cold night sky. He was forced to wake every 2 hours to replenish the fire with fresh logs. Even then, ice formed in his water bucket just 6 feet from the hearth. This problem wasn't unique to Samuel's construction. His nearest neighbor, Thomas Henley, had built his cabin using the same manual and suffered the same failures. Henley's wife lamented that their children huddled 3 to a bed under buffalo robes while the adults took turns tending the fire throughout the night. Further down the ridge, the Kowalski family had abandoned their fireplace altogether, moving their sleeping quarters into the root cellar, where the earth provided more consistent warmth than their regulation heating system. Samuel, having served 2 years with the Corps of Engineers before claiming his homestead, possessed a military-trained mind that questioned systems that failed under real-world conditions. When standard procedures consistently resulted in predictable failure, experienced soldiers sought alternatives. By February, Samuel was analyzing the problem with an engineer's precision rather than a homesteader's desperation. The waste was glaringly obvious once he quantified it. Using a mercury thermometer borrowed from the territorial surveyor, Samuel measured the temperature of the smoke as it exited his chimney, a staggering 160 degrees on a frigid night when the outside air was 12 degrees below zero. Simple math revealed the truth. Every cubic foot of that superheated smoke carried enough thermal energy to warm his cabin, yet the conventional system simply dumped it into the atmosphere. The Army manual had, in effect, designed a heating system that functioned as a heat disposal system. Samuel's thinking was influenced by more than just military engineering. His grandfather had immigrated from Bavaria, where winters were equally severe, but heating methods had evolved over centuries of necessity. Bavarian farmhouses utilized masonry stoves that burned wood in a firebox, but channeled smoke through interior walls before venting it outside. The underlying principle was thermal mass. Stone and brick absorb heat from the combustion gases and radiated that warmth slowly over many hours. Even more importantly, Samuel had spent his first year in the Michigan Territory working alongside Ojibwe guides, who shared their ancestors' methods for heating winter shelters. Their earth lodges and bark houses incorporated principles absent from any Army manual, using the ground itself as thermal storage, designing structures to retain heat rather than allowing it to escape, and building fires that served multiple purposes beyond just providing immediate flame. These influences coalesced in Samuel's mind during a particularly brutal cold snap in March, when his regulation fireplace consumed half a cord of wood in just 3 days yet failed to prevent his remaining potatoes from freezing solid. If Bavarian masons could capture heat in stone walls, and if Ojibwe builders could use earth as thermal storage, then perhaps the solution wasn't to generate more heat, but to waste less of what he already produced. The idea that emerged was radical by frontier standards, but entirely logical from an engineering perspective. Instead of allowing hot smoke to escape directly up the chimney, Samuel would force those combustion gases to travel through a system that captured their thermal energy. He would dig a tunnel beneath his cabin floor, line it with stones, and channel the smoke from his firebox through this underground passage before venting it outside. The heated stones would then store thermal energy and radiate warmth upward through the floorboards long after the fire had died. When Samuel explained his plan to Thomas Henley, his neighbor's response was immediate and dismissive. "You want to dig a tunnel under your house? That's the most foolish waste of labor I ever heard. The Army manual works fine if you just burn enough wood." Henley's wife was even more blunt. "Sounds like you're trying to turn your cabin into an Indian lodge. We came here to build civilized homes, not live like savages." The criticism reflected a deeper conflict between established methods and frontier adaptation. The Army Corps of Engineers had codified building practices that worked well in settled regions with abundant fuel supplies and moderate climates. However, when those same practices were transplanted to the resource-limited and extreme weather conditions of the northern frontier, they consistently failed. But admitting that failure meant acknowledging that official guidance was inadequate, and most homesteaders preferred to blame their own execution rather than question the system itself. Samuel understood this resistance, but had moved beyond caring about neighborly approval. His engineering background had taught him that successful systems were measured by results, not by conformity to established practices. If his underground heating system could reduce wood consumption while increasing thermal comfort, then the method was sound, regardless of how unconventional it appeared to others. The social cost of innovation, Samuel realized, was often higher than the technical cost. Building an underground smoke tunnel would require perhaps 30 hours of digging and stonework, and enduring the skepticism and mockery of his neighbors might prove even more challenging than the physical labor itself. Samuel began construction on April 15th, when the ground had thawed sufficiently for digging but before spring planting demanded his full attention. The tunnel route ran 20 feet from his fireplace foundation to a point beyond the cabin's north wall, following a precise 3-degree downward slope to ensure proper smoke flow without allowing backdraft. This gradient was critical. Too steep, and the hot gases would rush through without transferring heat to the stones. Too shallow, and smoke would pool and reverse direction during windy conditions. The excavation involved removing 18 cubic yards of clay and sandy soil, work that Samuel completed in sections to prevent cave-ins. He dug the tunnel 18 inches wide and 20 inches deep, dimensions carefully calculated to provide sufficient volume for smoke passage while maintaining structural integrity under the weight of the overlying earth. Each morning, he would excavate a 4-foot section, line it temporarily with split logs, and then move to the next segment. This systematic approach prevented the tunnel walls from collapsing and allowed him to maintain the precise slope throughout its entire length. Stone selection proved as important as excavation technique. Samuel had learned from Ojibwe builders that certain rocks held and released heat more effectively than others. Granite and basalt from the lake shore possessed high thermal mass, but were prone to cracking when heated too rapidly. Sandstone heated evenly, but crumbled after repeated heating cycles. The optimal choice was fieldstone limestone, abundant in local fence rows, which heated gradually and retained thermal energy for extended periods without structural failure. Samuel arranged the limestone in a specific pattern learned from his grandfather's descriptions of Bavarian construction. Instead of simply filling the tunnel with loose stones, he created a structured heat exchange system. The bottom third of the tunnel held fist-sized stones packed tightly to form a stable foundation. The middle section contained larger stones, each weighing 15 to 20 pounds, positioned to create air gaps that allowed smoke to circulate around their surfaces. The top layer consisted of flat stones that formed a crude arch supporting the tunnel roof, while maximizing surface area exposed to the passing smoke. A critical innovation was the baffle system Samuel designed at 3 points along the tunnel. Using flat stones positioned at 45-degree angles, he created obstacles that forced the smoke to change direction and slow its passage. These baffles prevented the hot gases from racing through the tunnel without transferring their heat to the surrounding stones. The design borrowed from principles Samuel had observed in beaver dams, where strategically placed obstructions controlled water flow and created pools of varying depths and temperatures. Construction of the tunnel exit required particular attention to draft management. Samuel built a vertical chimney shaft at the tunnel's end, rising 4 feet above ground level, but only 2 feet above his cabin roof. This height differential created enough draw to pull smoke through the underground passage, but not so much that the gases moved too quickly to deposit their heat. A simple stone cap, with 4-inch openings on opposite sides, allowed smoke to escape while preventing rain from entering the system. Samuel's first test came on a cold morning in early May, when overnight temperatures dropped to 28 degrees. He built a modest fire in his fireplace using 2 armloads of split oak and observed the smoke's journey through his underground system. The initial flow was sluggish, requiring him to open the cabin door briefly to establish proper draft. Once the system began drawing correctly, smoke moved steadily through the tunnel, emerging as a thin stream from the external chimney rather than the thick column that had previously poured from his fireplace. Temperature measurements revealed the system's effectiveness immediately. Using his mercury thermometer, Samuel recorded readings at multiple points along the tunnel during the test burn. At the tunnel entrance, smoke measured 140 degrees. Midway through the passage, the temperature had dropped to 90 degrees as thermal energy transferred to the surrounding stones. At the exit point, smoke registered only 60 degrees, proving that the limestone had absorbed most of the combustion heat. More significantly, the heated stones continued radiating warmth long after the fire had died. Samuel measured floor temperatures above the tunnel at hourly intervals throughout the night and the following day. 6 hours after the fire extinguished, the floorboards directly above the tunnel registered 72 degrees, while areas away from the tunnel measured 58 degrees. 12 hours post-fire, the tunnel zone maintained 68 degrees. Even 18 hours later, when the outside temperature dropped to 35 degrees, the floor above the heated stones remained at 62 degrees. The thermal performance exceeded Samuel's calculations. His engineering estimates had predicted that the system would extend heating duration by perhaps 8 to 10 hours. Instead, the limestone thermal mass provided measurable warmth for a full day and night, fundamentally changing the heating requirements for his cabin. Rather than stoking fires every 2 hours throughout the night, Samuel could build one substantial fire each evening and wake to comfortable temperatures the next morning. Wood consumption dropped dramatically once Samuel refined his firing technique. Previously, maintaining overnight warmth required burning 6 to 8 pieces of split hardwood every 2 hours, consuming roughly 1 cord per month during winter. With the underground system, Samuel discovered that a single evening fire using 12 pieces of wood provided equivalent heating through the following day. Monthly wood consumption fell to less than half a cord, representing savings of nearly 4 cords over a typical heating season. The system demanded specific maintenance procedures that Samuel developed through trial and observation. Every 2 weeks, he removed ash buildup from the tunnel baffles using a long-handled wooden scraper fashioned from a broken axe handle. Monthly cleaning involved removing loose debris from the tunnel floor and checking the external chimney cap for blockages. Annual maintenance required removing and repositioning stones that had shifted due to thermal expansion, a process that took half a day but ensured continued efficiency. Samuel's success attracted attention from unexpected quarters. Joseph Kingbird, an Ojibwe elder who occasionally traded at the territorial post, examined the tunnel construction during a visit in late spring. Kingbird nodded approvingly at the stone arrangement and explained that Samuel had unknowingly recreated heating principles that Anishinaabe builders had used for generations in earth lodges. The technique of using underground thermal mass was ancient knowledge, Kingbird explained, though Samuel's application to a log cabin represented a novel adaptation of traditional wisdom to frontier conditions. Samuel discovered the limitations of his underground heating system during the brutal cold snap of January 1847, when temperatures plunged to 30 below zero for 6 consecutive nights. Despite the tunnel's efficient heat storage, cold penetrated through his cabin walls with such intensity that frost accumulated on the interior logs, and his water bucket froze solid despite sitting directly above the heated tunnel. The thermal mass provided excellent heat retention, but the cabin envelope itself was hemorrhaging precious warmth faster than any heating system could replace it. The problem became quantifiable when Samuel used his mercury thermometer to measure temperature variations throughout the cabin during peak cold conditions. While the floor above the tunnel maintained 65 degrees, the temperature dropped steadily with distance from the heated zone. At shoulder height near the exterior walls, the thermometer registered 42 degrees. Near the ceiling, where heated air should naturally rise, temperatures fell to 38 degrees. The cabin's interior climate varied by nearly 30 degrees despite the underground system's steady heat output. Samuel recognized that heat loss occurred through multiple pathways simultaneously. Convective currents carried warm air upward toward the roof, where it escaped through gaps between the logs and around the chimney penetration. Conductive heat transfer moved thermal energy directly through the log walls to the frigid exterior air. Radiant heat loss occurred when the warm interior surfaces transferred energy to the cold walls and ceiling. His heating system was fighting a battle on 3 fronts, and thermal mass alone could not address the structural heat losses. The solution required understanding principles that frontier construction manuals ignored entirely. Samuel's conversations with Joseph Kingbird had introduced concepts of thermal barriers and dead air spaces that Anishinaabe builders had perfected over generations. Earth lodge construction used multiple layers of different materials to create insulating barriers that trapped air and prevented heat transfer. Kingbird explained that still air was nature's most effective insulator, but only when confined in small pockets that prevented convective circulation. Samuel began experimenting with insulation materials available on his homestead. Prairie grass, cut in late autumn when the stems were dry and hollow, provided excellent air-trapping capability when bundled tightly between wooden frames. Cattail fluff, harvested from the marshy areas near the lake, contained thousands of tiny air pockets that resisted heat transfer when packed into fabric casings. Bear fur, obtained through trade with local hunters, offered superior insulating properties due to its dense undercoat structure that trapped body heat in living animals. The most effective material proved to be a mixture Samuel developed through systematic testing. He combined chopped straw with clay slip and deer hair obtained from a tanning operation at the territorial post. When mixed in the proper proportions, 1 part clay to 3 parts straw to 1 part hair, the combination dried into a lightweight, fibrous material that could be packed into wall cavities. The clay provided structural integrity and moisture resistance. The straw created air pockets, and the animal hair added flexibility that prevented cracking as the material expanded and contracted with temperature changes. Application of the insulation required modifying the cabin's interior construction without compromising structural integrity. Samuel built a secondary wall system using vertical strips of split cedar attached to the interior surface of his log walls. These furring strips created a 3-inch cavity that he filled with his straw clay hair mixture, working from bottom to top in 4-foot sections. Horizontal boards salvaged from shipping crates provided the interior finished surface, creating an enclosed insulation system that prevented air circulation while allowing the mixture to remain dry. Ceiling insulation presented greater technical challenges due to the need to support the insulating material against gravity while maintaining access to the roof structure. Samuel solved this by installing a suspended ceiling system using lightweight poles tied with rawhide to create a grid pattern 18 inches below his roof beams. Over this framework, He spread canvas salvaged from military surplus tents, forming a shallow basin that he filled with loose cattail fluff to a depth of 8 inches. The suspended system reduced ceiling height, but created an insulating airspace that dramatically reduced heat loss through the roof. The floor required a different approach since Samuel could not disturb his existing tunnel system. He constructed a raised floor using split logs as joists, creating a 6-inch airspace above the original cabin floor. This cavity he filled with a mixture of dried leaves, grass, and wood chips obtained from his lumber preparation activities. Pine boughs layered between the organic materials prevented settling while adding their natural oils that repelled insects and rodents. Samuel's first comprehensive test of the insulated cabin occurred during a February blizzard that brought temperatures of 22 below zero with sustained winds of 30 miles per hour. The difference was immediately apparent. Interior temperatures throughout the cabin remained within 8 degrees of each other, ranging from 68 degrees near the tunnel to 60 degrees at the far corners. More importantly, these temperatures remained stable throughout the night without additional firing, something impossible before the insulation installation. Fuel consumption measurements revealed the insulation's economic impact. During the coldest month of winter, Samuel's wood use dropped from the half cord required by his tunnel system alone to less than 1/3 of a cord with the addition of comprehensive insulation. The thermal barrier effect meant that heat generated by his underground system remained inside the living space rather than escaping through the building envelope. Each British thermal unit produced by burning wood now provided heating for extended periods rather than quickly dissipating to the exterior. The insulation system required specific maintenance procedures to preserve its effectiveness over time. Samuel discovered that moisture infiltration was the greatest threat to insulating performance. He developed a routine of checking interior wall surfaces monthly during the heating season for signs of condensation that could dampen the straw clay mixture. Annual maintenance included removing and replacing any insulating material that showed signs of mold or pest infiltration, typically less than 10% of the total installation. Construction of the insulated cabin attracted attention from Swedish immigrants who had recently settled 15 miles east near the lumber camp. Lars Anderson, who had built traditional Swedish log homes with thick walls and small windows, recognized Samuel's techniques as adaptations of Scandinavian building practices his grandfather had used in northern Sweden. Anderson explained that Swedish builders had learned over centuries that insulation was more important than wall thickness in extreme cold climates. The Swedish connection provided Samuel access to additional traditional knowledge about moisture management and air sealing techniques. Anderson showed him how to use pine resin mixed with oakum to seal gaps around windows and doors, creating airtight barriers that prevented heated air from escaping while keeping cold drafts from entering. This final refinement reduced Samuel's heating requirements by an additional 15%, bringing his total wood consumption to less than 1/4 of what neighbors used in uninsulated cabins with conventional heating systems. Samuel's first spring with his completed heating and insulation systems revealed a problem he had not anticipated during winter construction. Snowmelt from his cabin roof created a continuous flow of water that pulled against the foundation logs and soaked into the ground directly above his underground tunnel. As temperatures fluctuated between freezing and thawing throughout March and April, this saturated soil expanded and contracted in cycles that gradually shifted the carefully positioned limestone in his tunnel system. The foundation moisture problem became critical when Samuel noticed that sections of his floor above the tunnel no longer maintained consistent temperatures. Areas that had previously registered 65 degrees during cold nights now measured only 58 degrees, indicating that thermal transfer from the heated stones had diminished. Investigation revealed that groundwater had infiltrated the tunnel through gaps between shifted stones, creating pockets of mud that insulated rather than conducted heat from the limestone to the cabin floor. Samuel recognized that water management required the same systematic approach he had applied to heat retention and insulation. Successful frontier construction demanded understanding how different natural forces interacted with building systems over seasonal cycles. His underground tunnel functioned perfectly as a thermal system but had created vulnerabilities in foundation drainage that conventional cabin construction avoided by keeping heating systems entirely above ground. The solution came from observing how water moved across his homestead during different weather conditions. Samuel spent 2 weeks in early spring tracking drainage patterns, noting where snowmelt collected, where the ground remained saturated longest, and where natural slopes directed surface water. He discovered that his cabin sat at the convergence point of 3 minor drainage channels that carried runoff from higher ground during spring thaws and heavy summer storms. French drainage techniques learned from conversations with territorial surveyors who had worked in Louisiana provided the foundation for Samuel's water management system. The principle involved creating underground channels that intercepted groundwater before it could reach building foundations, directing it away through gravel-filled trenches that maintained flow even when the surrounding soil became saturated. Samuel began by digging a drainage trench around the uphill perimeter of his cabin, following the natural contours that directed water toward his foundation. The trench measured 18 inches deep and 12 inches wide, following a consistent 2-degree slope that ensured water would flow toward a collection point 50 feet from the cabin. This gradient was crucial. Insufficient slope allowed water to pool in the trench, while excessive slope caused erosion that would eventually undermine the drainage system. The trench required specific layering to function effectively throughout seasonal changes. Samuel placed large field stones, each weighing 10 to 15 pounds, along the bottom to create a stable foundation that would not shift during freeze-thaw cycles. Over these foundation stones, he laid a 6-inch layer of gravel ranging from pea-sized to walnut-sized pieces, sorted to ensure proper water flow without allowing fine particles to clog the drainage channels. A critical innovation was Samuel's use of split cedar logs to create a covered drainage system that prevented surface debris from entering the gravel channels while maintaining access for maintenance. He positioned half logs over the gravel layer with a flat side down, creating arched spaces that allowed water to flow freely while supporting the weight of the overlying soil. This technique borrowed from beaver dam construction principles Joseph Kingbird had described, where overlapping materials created strong structures that channeled water flow without impeding it. Roof water management required a complementary system that intercepted precipitation before it reached the ground around the cabin foundation. Samuel constructed gutters using split logs hollowed with an adze, mounting them along. Here is the English, U.S., translation and interpretation of the provided text, written in a clear and engaging style. The cabin's eaves were lined with wooden brackets, meticulously crafted from oak branches. These served as gutters, ingeniously collecting rainwater and snowmelt from the entire roof and channeling it through wooden downspouts. The downspouts directed the water to designated collection points connected to an underground drainage network. Furthermore, the design incorporated sandstone splash blocks, each carefully carved to dissipate the water's energy as it exited the downspouts, thereby preventing soil erosion at these discharge locations. These blocks, measuring 2 feet in length and 8 inches in width, featured a shallow depression that effectively spread the concentrated water flow over a wider area. Samuel strategically positioned these splash blocks to direct the roof runoff into swales he had dug. These swales efficiently carried water away from the cabin foundation, following the natural contours of the land's drainage patterns. This drainage system was thoughtfully integrated with the existing landscape to ensure proper function even during extreme weather events. He created earth berms, utilizing soil excavated from his drainage trenches, and positioned these raised areas to divert surface water away from vulnerable zones surrounding his cabin. The berms followed the land's contour lines, effectively cooperating with the natural topography instead of opposing established drainage routes. The most sophisticated element of the system was a retention basin located 60 feet from the cabin, where all drainage channels converged. This basin, measuring 8 feet across and 3 feet deep at its center, served as a collection point for water from both the roof gutters and foundation drains during heavy rainfall or rapid snowmelt. Any overflow from the basin was directed towards a natural creek, ensuring the water was safely carried away from his homestead without causing erosion. The true test of the drainage system came during the spring floods of 1848. A week of unseasonably warm weather melted accumulated snow, while simultaneous rainfall contributed even greater water volume. Samuel's gutters and drains successfully handled the combined water load, preventing any moisture from accumulating against his cabin foundation. Temperature measurements taken above his tunnel system remained consistent throughout the flood period, confirming that the drainage improvements had indeed preserved the thermal performance of his underground heating system. The economic benefits of this proper drainage extended far beyond merely protecting Samuel's existing investments in heating and insulation. The dry soil around his cabin foundation prevented frost heaving, a common problem that damaged neighboring cabins. This saved him the considerable expense of releveling floors and repairing foundation logs that would otherwise shift during freeze-thaw cycles. The carefully controlled water management also presented opportunities for Samuel to establish a kitchen garden in areas where controlled irrigation from his retention system provided reliable moisture, even during dry periods. Samuel's drainage techniques attracted the attention of the territorial road supervisor, who recognized their potential for managing water flow around bridges and culverts, locations that frequently washed out during the spring floods. The supervisor hired Samuel to construct similar drainage systems at 3 critical road crossings, providing him with additional income that helped to offset the labor he had invested in developing his water management techniques. The integration of heating, insulation, and drainage systems created a cabin environment that functioned efficiently throughout seasonal extremes, requiring minimal maintenance and fuel. Samuel had effectively developed a comprehensive approach to frontier construction. He addressed multiple environmental challenges through coordinated technical solutions, each reinforcing the effectiveness of the others while drawing on traditional knowledge adapted to the specific local conditions. The winter of 1849 brought the most severe weather in territorial memory, as a massive Arctic storm system stalled over the Great Lakes region for 12 consecutive days in February. Temperatures plummeted to 41 degrees below zero, and sustained winds of 45 miles per hour created conditions that territorial officials later documented as unprecedented in frontier records. This storm provided the ultimate test of Samuel's integrated building systems against the most extreme environmental stress the northern climate could deliver. Samuel had prepared for severe weather by developing systematic procedures for storm operations, going beyond simply maintaining his heating system. He established protocols for monitoring system performance during extreme conditions, using techniques that allowed him to identify potential failures before they became critical. These procedures included hourly temperature readings at 16 specific locations throughout his cabin, daily inspection of drainage outflows for ice blockages, and careful tracking of wood consumption rates to detect any decline in system efficiency. This meticulous monitoring approach required Samuel to create measurement tools that provided accurate data even under harsh conditions. He fashioned temperature recording stations using mercury thermometers mounted in wooden frames at precise locations, floor level above the tunnel, shoulder height near exterior walls, ceiling level at the cabin center, and exterior readings taken through a small observation port he had installed in his north wall. Each station was marked with carved notches to ensure consistent positioning of the thermometers, even in darkness or during blizzard conditions. Samuel's fuel management strategy during the extended storm underscored the importance of system redundancy in extreme survival situations. Rather than relying solely on his efficient underground system, he prepared an auxiliary heating capability using a small metal brazier positioned to heat his sleeping area directly in case the main system failed. He stockpiled split kindling in graduated sizes, from pencil-thin starter wood to wrist-thick sustaining fuel, organizing these materials in a sequence that allowed rapid fire building without waste or delay. The storm's intensity revealed performance characteristics of Samuel's systems that had not been apparent during normal winter conditions. Wind-driven snow accumulated against his cabin walls to depths of 6 feet, creating insulation that actually improved his building's thermal performance by adding an exterior barrier that reduced heat loss through the log walls. The drainage system prevented this snow accumulation from creating ice dams that could force meltwater into his foundation when temperatures eventually moderated. Samuel's neighbor, Thomas Henley, faced catastrophic system failures during the 4th day of the storm when his conventional fireplace could not generate sufficient heat to prevent the interior from freezing. Henley's cabin interior temperature dropped to 18 degrees above zero, causing his water supplies to freeze solid and forcing his family to abandon their cabin for the relative warmth of their livestock barn. The Henley family's survival depended on body heat shared with their cattle and horses, a desperate measure that frontier families adopted only when their heating systems failed completely. The stark contrast became quantifiable when Samuel began recording comparative data between his cabin's performance and conditions in neighboring homesteads. During the storm's peak intensity, Samuel's interior temperatures ranged from 64 degrees near his tunnel system to 58 degrees at the cabin's extremities. Henley's cabin, measured during welfare check visits by Samuel, registered temperatures between 22 and 34 degrees, despite continuous firing of his conventional fireplace. Samuel's wood consumption during the 12-day storm totaled less than 1.5 cords, burned in controlled evening fires that provided heating for complete 24-hour cycles. Henley consumed 4.25 cords during the same period while achieving inferior results, demonstrating that Samuel's integrated systems provided nearly 3 times the heating efficiency of conventional frontier construction. These measurements, recorded meticulously in Samuel's daily log, provided quantitative proof of his method's superiority under extreme conditions. The storm's conclusion brought requests for technical assistance from homesteaders throughout the region, many of whom had witnessed the dramatic performance differences between Samuel's systems and conventional construction. 7 families approached Samuel during March 1849, seeking instruction in underground tunnel construction, insulation techniques, and drainage management. Samuel recognized that effective knowledge transfer required systematic teaching methods rather than simply casual explanations. Samuel developed a structured apprenticeship program that allowed other homesteaders to learn his methods through hands-on construction projects. Instead of attempting to explain complex thermal and structural principles through verbal instruction alone, Samuel required students to participate in actual building work, where they could directly observe cause and effect relationships. Each apprentice committed to working on Samuel's homestead for 2 weeks in exchange for instruction in specific techniques that they could apply to their own construction projects. The teaching process revealed aspects of Samuel's methods that he had developed intuitively but had never articulated systematically. When forced to explain his decision-making process to apprentices, Samuel recognized that his techniques followed consistent principles that could be applied to a variety of frontier construction challenges. These principles included working with natural forces rather than against them, using multiple reinforcing systems instead of depending on single solutions, and adapting traditional knowledge to local conditions through systematic experimentation. Documentation of Samuel's techniques began when territorial surveyor James Crawford recognized their potential applications to government construction projects. Crawford arranged for detailed drawings and written specifications to be prepared by the Territorial Engineer's Office, creating the first technical manual that described underground thermal mass heating adapted to North American frontier conditions. These documents were distributed to Army posts and territorial offices throughout the northern frontier regions. Samuel's innovations influenced construction practices far beyond his immediate region when territorial officials incorporated his drainage and heating techniques into standard specifications for government buildings. Military posts constructed after 1850 routinely included modified versions of Samuel's underground heating systems, and territorial courthouses and land offices adopted his insulation methods for improved fuel efficiency and occupant comfort. The legacy of Samuel's integrated building approach extended into the 20th century through homesteaders who carried his techniques westward during later territorial expansion. Norwegian and Swedish immigrants who learned Samuel's methods in Michigan applied them to construction in Minnesota, Dakota Territory, and eventually Alaska, where extreme climate conditions made efficient heating systems essential for survival. Modern off-grid construction continues to rediscover principles that Samuel developed during his frontier experiments with thermal mass, passive solar design, and integrated building systems. Contemporary builders working in remote locations face identical challenges of fuel scarcity, extreme weather, and limited resources that Samuel addressed through systematic application of traditional knowledge adapted to specific environmental conditions.